Chapter 15, Acid-Base Equilibria. This is a really important chapter in this particular book. It's probably the one that's most heavily tested on the exam. So make sure to take good notes, to read the book carefully, and to do lots of practice. The first section is about solutions of acids or bases that contain a common ion. Now we've already done the common ion in another chapter. Remember, the shift in equilibrium position changes when we have an ion that we are adding that is in common with an ion in the equation. We can remember this as Le Chatelier's principle. So if we have an ion that's in common with something already in the equation, it's going to shift away from that because it's going to be a stressor to that reaction. So for example, here is HCN and water producing the hydronium ion and Cn negative. If I add NaCN, notice NaCN, when I write it out, is Na positive and Cn negative. When it breaks apart, you'll notice the ion that it has in common with the one in the equation is Cn negative. So it's as if I'm adding more cyanide ion. When I do, the reaction is going to shift back towards the left. And you'll notice it says a solution of HCN and NaCN is less acidic than a solution of HCN alone. And that makes sense because of course the H3O ion, which is the major contributor of the pH, the hydrogen ion, if we add more cyanide, it's going to shift to the left, and that shifts away from the production of those hydronium ions. So let's talk about solutions that are buffered. You may have heard about buffering in biology. It's an important process, especially in our body. What are the things we have to know about buffered solutions? What is buffering? And how can we work with that in chemistry? Buffered solutions are solutions that resist a change in pH. Important. So if you, in your stomach, for example, if you eat a lot of acidic food, you don't want to have your stomach extremely acidic. Or if you eat some sort of food that's very basic, you want your stomach acid to be able to effectively deal with the change in pH in your stomach. So what happens is what's called buffering. It's a situation that resists change in pH. What are buffers? They're usually weak acids or bases that contain a common ion, or their conjugate, as we would say. After addition of a strong acid or base, what happens is they resist change in pH. So how do we solve these problems? We look at the stoichiometry first, and then the equilibrium second. So here's an example of a solution of buffering. Now we're not going to actually solve this one, I believe. I think it's just showing some information. And then we'll actually solve one later. I believe. We'll look at it. I can't remember. But let's see. What is the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? You notice sodium acetate has an ion in common with this particular acid. And the Ka for acetic acid is 1.8 times 10 to the negative 5. All right, so how are we going to do this? And I guess this is one I am going to solve. I forgot. I was reading ahead in the PowerPoint slide, and I'm thinking of something else. So do not worry. We will come to another one where we're just going to talk about it. So in this case, here's acetic acid, HC2H3O2. You could write water if you prefer, but I'm just going to write hydrogen and C2H3O2 negative. So in this case, because it's a weak acid, of course we're going to solve using ice. We know that it's 0.45 molar. 0.45 molar. Now, you notice the sodium acetate will produce sodium ions and acetate ions. Whoops. And C2H3O2, I've got that wrong. Let me put that back. And because salts will ionize 100%, sodium acetate will break apart into ions 100%. So therefore, if the concentration of sodium acetate is 0.85 molar, concentration of sodium is 0.85 molar, as well as acetate. And that becomes important because when it's dissolved in a solution of vinegar, which is aqueous, that means that now we have 0.85 molar acetate ions initially, in the beginning. We don't have any hydrogen ions, but we have acetate ions, which is unusual. Usually we have no products and all reactant. So this is how this chapter is a little bit different. All right, we're going to continue on, and we don't know the change, but we know that at equilibrium we have 0.45 minus X of the acetic acid, we have X hydrogen, and we have 0.85 plus X of the acetate ions. All right, how are we going to solve this problem? Well, pretty easily. We know that Ka, which is 1.8 times 10 to the negative 5, is equal to the products over the reactant, and using our equilibrium row, we would say it's X times, whoops, 0.85 plus X over 0.45 minus X. So just using the information from up here. And like before, because we assume that the value of X is going to be much smaller than these other numbers, 0.45 and 0.85, we're going to get rid of them here and here. And you notice we set up kind of a ratio. Essentially, we're going to solve for X, and when I did, I got 9.52 times 10 to the negative 6. That is the concentration of hydrogen ions. And of course, we want the pH. So the pH is the negative log of that number that we just got there. And when we work it out, we get, I got 5.02 as they're showing here as the answer. Very easy, very straightforward. Now, you'll notice because we have some reactant and some products every single time, there is going to be a new equation that can help us. Now these new equations, this new equation that's coming up on the next slide, is only applicable for buffered solutions. You can't do it with the things that we learned in the previous chapter. So let me show you an example of the equation. I'll show you what it is. It's actually on your cheat sheet. It's called the Henderson-Hasselbalch equation. It's a very useful equation if you know when to use it. Here it is. This actually jumps right to what is the pH. pH is equal to the pKa. Now P, remember, is negative log. In chemistry, the lowercase p means negative log. So this is the negative log of the Ka value plus log of A negative over HA. I think of it as products over reactant. So A negative is one of the products of the reaction, and HA is the concentration of the acid. I believe your cheat sheet actually has a POH value, Henderson-Hasselbalch equation too. You can look that up and see what that is. So how would the Henderson-Hasselbalch equation be used to solve the previous question? Now you saw, let me just go back. Okay, there's the previous question. We had no problem solving it using ice. Well, you can use that every single time. In fact, I've had students over the years who prefer to use ice every time because then they don't have to figure out, can I use the Henderson-Hasselbalch equation? But if you know when to use the Henderson-Hasselbalch, it saves a tiny bit of time to use it. So let me show you how we would solve this exact question. I'm going to move away from it now, using this Henderson-Hasselbalch equation. So how to do that? All right, we're going to plug into the formula, and the pH equals the negative log of the pKa, so, or the Ka, pardon me, which is 1.8 times 10 to the negative 5. And to that you're going to add log of the concentration of the products, in this case 0.85, you'll remember, and the other is 0.45. On the previous question when we solved it, you might remember, if you look back, that it was the two concentrations were actually divided, and that you were eventually solving for x and then finally pH by taking the negative log. So this is kind of all in one. When I did this, I got 4.744. I didn't do too much rounding for this. And the log of 0.85 over 0.45 was 0.276. And of course, when I worked it out, I got 5.02. So therefore, you can see that whether you use the Henderson-Hasselbalch equation or you just prefer to use the ICE chart, you can get the same answer. Oops, and now I have totally blocked this. Let's see. I will erase what I wrote so we can read it. And it says, for a particular buffering system, a conjugate acid-base pair, like we just had, all solutions that have the same ratio, A minus to HA, will have the same pH. Okay. So let's see what they say about solution characteristics. Important facts. Buffers contain relatively large amounts of weak acid and corresponding conjugate base. So it's a weak acid and its conjugate, or a weak base and its conjugate. Added hydrogen reacts to completion with the conjugate base. The added OH negative ion reacts to completion with the weak acid. And then the pH in the buffered solution is determined by the ratio of the concentrations. As long as the ratio remains constant, the pH will remain constant. But this will be the case as long as the concentrations of the buffering materials are large compared with the amounts of hydrogen or hydroxide added. Most of the time, we're not going to be talking about theory of this. The questions that you will see will be actual math problem solving. So if you can solve the problem, that's all you really need to do. Other information: the amount of protons or hydroxide ions in the buffer can absorb without a significant change in pH. That's what a buffer is, of course. And of course, this is determined by the size of the concentration. So the more concentrated these solutions and their conjugates are, that's going to determine the amount of the pH and the change of pH. A buffer with a large capacity contains large concentrations of the buffering components. So the more concentrated they are, the more they can buffer. Optimal buffering occurs when HA is equal to A negative. So those two numbers are the same. And of course, if you think mathematically, log of a number over itself is log of log of 1, which is 0. So the pH should equal the pKa. Let's see what it says. It is for this condition that the ratio is more resistant to change when hydrogen or hydroxide is added to the buffered solution. And so here we go. The pKa of the weak acid to be used in the buffer should be as close as possible to the desired pH, because if the pH equals the pKa, that's the perfect ratio.